Good morning, students. So in the 8th unit, next we pass on to the internal energy. So internal energy of thermodynamic system is nothing but sum of the kinetic and potential energies of all the molecules of the system. So with respect to its center of mass of the system, here the energy due to the molecular motion, including the translational, rotational and vibrational motion, is called as an internal kinetic energy. So the energy due to molecular interaction is called internal potential energy. That is, example is nothing but a bond energy. So U is equal to Ek plus Ep. Since ideal gas molecules are assumed to have no interaction with each other, so the internal energy consists of only one kinetic energy part, which includes on the temperature, number of particles and is independent of volume. So however, this is not true for a real gases like a van der Waals gases. Internal energy is a straight variable. It depends only on the initial and the final states of the thermodynamic system. For example, if the temperature of water is raised from 30 degrees Celsius to 40 degree Celsius, either by heating or by stirring, then the final internal energy depends only on the final temperature, that is 40 degrees Celsius, and not the way it is arrived at. Next, we pass on to the Joules mechanical equivalent of heat. The temperature of an object can be increased by heating or by doing some work on it. So, in the 18th century, James Prescott Joule showed that the mechanical energy can be converted into internal energy and vice versa. So, in his experiment, two masses were attached with the rope and the pedal has a wheel. So, when these masses fall through a distance h due to the gravity, both masses lose its potential energy. So we know that if it falls to the distance, that means from the height to the gravity, if it comes down, if any object has to be fall from the height to the ground, then obviously its potential energy will be decreases. So here also, due to that, both the masses loses its potential energy, that is equal to 2 mgh, because two masses we have took. That's why we are losing 2 mgh. When the masses fall, the pedal wheel turns. Due to the turning of wheel inside water, so frictional force comes in between the water and the pedal wheel. So this causes that. So this is an experimental one, and this causes a rise in the temperature of the water. So this implies that the gravitational potential energy is converted as an internal energy of water. So the temperature of water increases due to the work done by the masses. So in this fact, the Joule was able to show that mechanical work has the same effect of the giving heat. So he found that to raise 1 gram of an object by 1 degree Celsius, so 4.186 joule of energy is required. So in earlier days, the heat was measured in calories. So 1 calorie is equal to 4.186 joule. So this is called Joule's mechanical heat, mechanical equivalent of heat. Understood how they are getting this rise in temperature? Next, we pass on to the first law of thermodynamics. So first law of we already discussed the zeroth law of thermodynamics. So first law of thermodynamics is a statement of a law of conservation of energy. So in Newtonian mechanics, conservation of energy involves, what is the conservation of energy? Kinetic and potential energy together, so of bulk objects. And but first law of thermodynamics includes heat also, that is the difference. So this will be states that change in internal energy, that is a del U of a system, is equivalent to the heat supplied of the system minus the work done by the system on the surroundings. Okay, so what is the internal energy? It's equal to the heat supplied to the system minus work done by the system. So this is the zeroth law of thermodynamics, and for that they are given the diagrams also. We'll see that. So what is the internal energy? Del U is equal to Q minus W. Q is nothing but, what is Q? That is a heat. Okay, heat given to the system, and W is a work done by the system. So internal energy of a thermodynamic system can be changed either by heating or by work. So heat flows into the system, internal energy increases. Heat flows out of the system, means internal energy decreases. Like that, work is done on the system, internal energy will increase. work is not done on the system, work is done by the system means the internal energy is decreases. So based on the above table, the sign convention is introduced to use the first law of thermodynamics appropriately. So, and this will be given as system gains heat means Q is positive, system lost the heat means Q is negative. Work done on the system is W is negative, work done by the system is W is positive. So like this they are given the diagram also as a sign convention. Okay, so what is given? Q is greater than 0, W is also greater than 0. When Q is greater than 0, W is lesser than 0. So in this case, and what is the next one? Q is lesser than 0 means W is lesser than 0. Q is lesser than 0, W is greater than 0. So these are the sign conventions. So even though we often explain the first law of thermodynamics using the gases, this law is universal and applies to the liquids and solids also. Okay, understood what they are given here. So it's a first law of thermodynamics. Next we pass on to the quasi-static process. So for this we are going to consider a system of an ideal gas that should be kept in the cylinder, and its volume is V, and we are taking the pressure as to be P and the temperature is T. So what happened means, when the piston is attached to the cylinder, that moves outward, outward the volume will change. Okay, the outward the volume of the gas will change. So as a result, the temperature and pressure will also change, because all the three variables P, T and V are related to the equation. We know the ideal gas equation. What is ideal gas equation? PV is equal to NKT. So if a block of some mass is kept on the piston, it will suddenly push the piston down. So the pressure near the piston will be larger than the other parts of the system. So it implies that the gas is in the non-equilibrium state. We cannot determine the pressure or temperature or internal energy of the system until it reaches the another equilibrium state. But if the piston is pushed very slowly, such that at every stage it will be still in the equilibrium with the surrounding. So we can use the equation of state to calculate the internal energy, pressure or temperature. So this kind of process is called as an quasi-static process. So a quasi-static process is infinitely slow process in which the system changes its variable, that is PVT, and slowly it remains in a thermal, so mechanical and also the equilibriums and its surroundings throughout. So by this infinite slow variation, the system almost choose to equilibrium states. So if it is equilibrium, then only we are able to find the changes in the pressure, volume and temperature. If it is in the non-equilibrium position, so no change has to be happened. That is the quasi-static process. So for maintaining that static, the system has to be always in equilibrium position. That is a quasi-static process. And next we pass on to the work done in a volume changes. So consider the gas contained in the cylinder fitted with the movable piston. Suppose the gas is expended quasi-statically by pushing the piston by a small distance dx. So what happened? The expansion occurs quasi-statically. The pressure, temperature and internal energy will have the unique values at very instant. Okay, and the small work done by the gas on the piston, so that is, we know that if work done has to be in the system, what is the work done? F into ds, that is the distance, the force exerted by the gas on the piston. So if there is a force, there will be a pressure. So what we are getting? F is equal to pressure into area, because pressure is equal to force by area. So here A is the area of the piston and P is the pressure on the piston. Pressure of the gas on the piston. So what is the equation now? What is the value of F? PA. So we are substituting that in the equation. We will get dW is equal to PA dx. So what is A dx? That is area into distance, is nothing but that is equal to dV. That is the change in volume during the expansion process. So the small work done by the gas during the expansion is given by dW is equal to PdV. Here dV is a positive since the volume is increased. If dW is positive, in general the work done by the gas is increasing the volume Vi to Vf, that is initial to final, and we are taking that as an integral value. Okay, so what we are getting, suppose a work is done when V, that is initial, is greater than final, then the W is negative. Note here the pressure is inside the integral in equation, so it implies that while the system is doing work, the pressure need not to be a constant. So evaluate the integration, we need to first express the pressure as a function of the volume and temperature using the equation of system. So here what happened means the pressure, if we are calculating with the volume, but the pressure inside of it should be a integral one. So first we have to make that pressure need not to be a constant one, then only we are able to find the integration that is given in the work done. And next we pass on to the PV diagram, that is a pressure volume diagram. So is a graph between the pressure and the volume of the system. So PV diagram is used to calculate the amount of work done by a gas during the expansion or on the gas during the compression also. So in the unit 2 we discuss the area under the curve will give the integration of the function from the lower limit to the upper limit. So the area under the PV diagram will give the work done during the expansion or the compression, which is like this it will give. Okay, see the graph. So what is the final and the initial values of the pressure and volume, we are plotting the graph for that one. Okay, and from this we are going to make the value. So that is the shape of PV diagram depends on the nature of the thermodynamic process. Understood? So this will give the work done by the gas. So pressure and volume will give the work done by the gas. Understood this one?